I am Saraj Punishedwai and I am pursuing electrical engineering from JHRC Nagpur. I am honored to present our latest project, the Electrical Vehicle Prototype 201, which represents a significant step forward in sustainable transportation technology. It has been both a challenging and a privilege to lead this endeavor, and I am excited to share our progress with you today. Using a single cell, two neodymium magnets, a copper coil, and two pins. This motor operates based on Faraday's law of electromagnetic induction. Set up three copper coils are strategically positioned 120-degree apart, complemented by a single bearing and two neodymium magnets. Additionally, the system incorporates three push buttons. This configurations from a brushless DC BLDC motor where each button corresponds to magnetizing one of the coils to attract the magnet. As per Faraday's law of electromagnetic induction, this motor operates in a continuous cycle. Using three MOSFETs and an Arduino board, this setup automates coil operation. The MOSFETs acting as automated push buttons, receiving signals from the Arduino, powering the three coils. This clip demonstrates the transitions from manual to fully automated operation. Through Arduino programming, MOSFETs activation is controlled, ensuring precise coil operation. The programmed logic guarantees coordinated functionality, enhancing system efficiency and reliability. In this configuration, three relays replace the MOSFET, serving as switch buttons controlled by the Arduino. Signals from the Arduino activate the relays, energizing the coils and initiating motor rotation. This adjustment highlights the adoption of relay-based coil activation. In this setup, signals are transmitted from the BMS Arduino to the motor Arduino. When a signal of 1 is embedded, the LED above the motor controller Arduino illuminates, and when a signal of 0 is embedded, the LED turns off. This LED serves as a reference point for communication between the two Arduinos. The motor configuration typically includes a rotor with a bearing, two powerful neodymium magnets, bolt made of mild steel, copper wires, and a blade of connections. The motor arrangement and wiring are depicted where the stator windings are wounded with a complete 200 turns of copper wire of a specific gauge to ensure the generation of a uniform magnetic field. When you supply DC current to one of the stator winding, for example, this it produces an electromagnetic field, generating a magnetic force. The force interacts with the permanent magnet's field of the rotor, creating torque that spins the rotor. As the rotor turns, the stator winding receives energy in a precise order, producing a rotating magnetic field that sustains the rotor motion. We are progressing to the next stage, which involves implementing a BMS, short for Battery Management System. This system is designed to manage and monitor a rechargeable battery pack or battery system. The primary responsibility of a BMS encompass self-monitoring, self-balancing, thermal regulation, communication, and facultating emergency motor start and stop functions. Data provided by the BMS includes battery voltage, individual cell voltage, battery current, battery temperature, and state of charge. Presently, the thermal management system within a BMS is tasked with overseeing the battery pack's temperature to maintain its safe and efficient operation within an optimal range. Its key components include temperature sensor, a cooling system, a heating system, and a control unit, all working together to regulate the battery pack temperature and ensure its reliability. The BMS includes BMS Arduino, current sensor, humidity sensor, fuse, kill switch, and a contactor. Tuning to the next crucial aspect of power generation, I2C communication. The, the setup for this connection is illustrated here. I2C communication protocols are employed to establish communication between a motor Arduino and a BMS Arduino, facilitating the exchange of data and commerce between the two. In this setup, BMS Arduino functions as the power master, enhancing communication and controlling the BMS bus. Meanwhile, the rotor control Arduino serves as the slave, responding to commands from the master. In the ultimate stage of constructing the motor controller, three printed circuit boards have been employed, each containing P and N channel MOSFETs, adhering to the providing instructions. N and P channel MOSFETs have been meticulously soldered into registers, and additional pins in the PCBs. In order to activate each winding, I have labeled them U, V, W, and respectively arranged the PCB connection according to achieve a specific rotational direction of the rotor. Instantaneous of the process involves activating MOSFETs Q1 and Q6, energizing coil U and W. While coil U generates repulse force on a magnet, coil W attracts a magnet. The opposing force with coil U repels and coil W attracts induce a push and pull motion, driving the motor rotation. Identical procedure is employed to energize the remaining coil and rotate the rotor through simulating activating and deactivating the coils. The motor operation is accordance with the predefined phase sequence. This essentially defines the motor's functionality. The challenges encountered during this process were attributed to uneven distance between the magnet and the poles, resulting in undesired repulsion and attraction. Furthermore, the rotor's inability to rotate was caused by loose jumpers connection. To address these issues, I adjusted the pole arrangement to ensure equal air gap and replaced the loose connection with secure jumper connections. This is how motor of my EV prototype works. Thank you guys.